The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
This week we're talking volcanoes, because there are few things that fascinate us more than the amazing, unstoppable power of an erupting volcano. A little later on, we'll speak to Janine Krippner, a postdoctoral researcher and volcanologist at Concord University in West Virginia, and learn about some of the lesser-known volcanoes in the U.S. But first, we turn to the Hawaiian volcano that's been making headlines, Kilauea. Hello and welcome to Science for the People. I'm Rochelle Saunders. With me is Jessica Johnson. Jessica is a lecturer in geophysics at the University of East Anglia in Norwich. She did her PhD in volcano seismology at Victoria University of Wellington in New Zealand, and a 2-year research fellowship at the Hawaiian Volcano Observatory and University of Hawaii at Hilo, and also a 2-year Marie Curie research fellowship at the University of Bristol. She teaches applied geophysics and geophysical hazards and researches volcano geophysics. Jessica, welcome to Science for the People.
Thank you.
So before we get into the most recent activity of the Kilauea volcano, can you give us a little primer on Kilauea before this spring?
Yes, so Kilauea is the most active volcano on the Big Island of Hawaii. It's the furthest south on the Big Island, and it's been in almost a constant state of eruption for about the last 35 years. Prior to this new activity, the activity was dominated by a lava lake at the summit of the volcano, which opened in 2008, and that lava lake sort of had convection in it and produced a lot of gas, but the lava itself didn't come out of the volcano. It came to the surface into the lake and then dropped back down again once it had degassed. The other eruptive site was called Pu'u'o'o, and that was about halfway down the rift zone, and this is the place where the lava often came out of the volcano, flowed over the surface down towards the ocean. So that eruption on the East Rift Zone has been going on for about 35 years, on and off. So what happened this spring was that the magma appeared to drain from those two eruption sites and travelled further along the rift zone and then started to erupt in the lower East Rift Zone.
Can you, before we get into the specifics of what happened this spring, can you talk a little bit about the type of volcano that Kilauea is? Obviously, I believe this is quite a popular area for tourists as well, who like to poke lava with sticks. So I'm assuming it's quite different from different types of volcanoes, for example, like the one that recently erupted in Guatemala.
Absolutely, yeah. So the types of volcanoes mostly depend on the type of magma that supplies the volcano. And there's a large spectrum of different types of magma. Kilauea is one end of the spectrum. It has a low silica content and high temperatures, and that usually means that it's quite runny. The fact that it's runny allows the gas to escape quite easily as bubbles, and that means that the lava itself has a lower gas content, again reducing the viscosity, the stickiness of the lava. That means that when there are eruptions, they're less likely to be explosive because the pressure can't build up because the gas can escape, and the lava tends to flow quite easily. The other end of the spectrum is when the magma is very, very sticky and the gas can't escape. And an example of that might be Yellowstone, where their eruptions are very infrequent. And when there is an eruption, it tends to be a lot larger and more explosive. Fuego volcano in Guatemala is somewhere in the middle of those. So it has fairly sticky lava, so it has explosions and produces ash rather than frequent lava flows in the way that we think of lava. And so that means that the eruptions tend to be more explosive and produce pyroclastic flows. Fuego itself is a bit different to other andesitic volcanoes. Andesite is the type of magma which is in between the spectrum, and Fuego actually erupts more frequently than a lot of other andesitic volcanoes because it has a higher supply rate.
A higher supply rate means that there's just more magma coming up to it?
Yes.
Why is that? Is it just on a particular magma-y part of the world, I guess?
I'm not sure, actually. I don't know about that area, but...
Fair enough. Can you talk a little bit about what makes Hawaii such a hot spot for volcanic activity? We've got a volcano that's been erupting for, I think you said, over 30 years.
Yeah. Well, it's exactly that. It is a hot spot. So the current thinking is that there is a source of hotter material deep in the earth, and that hotter material is less dense than the surrounding material in the mantle. And so that material rises to the surface and erupts. And that's different to other volcanoes that we hear about on the news. Most volcanoes happen at places where the tectonic plates of the Earth, so the surface of the Earth is split up into tectonic plates which kind of move slowly. And in some places those plates move away from each other, which cause a depressurization of the underlying mantle, and that's why you might get volcanoes in those places. An example of that is Iceland. Some places the tectonic plates move side to side, and that's where you often get really large earthquakes. So California is an example of that, but you don't usually get volcanoes in those areas. And some places the tectonic plates move towards each other, and one will go underneath the other. And the compression of that plate going underneath the other plate squeezes any water out of it, and the water rises up through the overlying plate and causes the overlying rock to melt, and that's why you get these more viscous, more explosive volcanoes. So an example of that might be Mount St. Helens in Washington. So that's where you usually get volcanoes. A hotspot volcano is different because it's often in the middle of a tectonic plate where we wouldn't expect a volcano to be, but it's caused by that hotter material punching through the middle of the tectonic plate. And often, in the case of Hawaii, the supply of magma from that hotspot is quite high, and that's why it's so eruptive.
So let's talk a little bit about Kilauea. On the scale of erupting volcanoes, is this considered to be a large eruption, what's been happening in Kilauea, or maybe medium size? I'm not quite sure what the spectrum of possible eruptions are. I would say it's difficult to kind of, there are different types of scales. So we often measure volcanic eruptions using an explosivity scale, and on that sort of scale it's very small because there haven't been large explosions. On the scale of the amount of volume produced, again, it's not actually that big. We see these videos of the rivers of lava and we think, wow, that's a lot of lava. But if you look on the map of Hawaii and look at the area that's been affected, it's quite a small area. So it's a fairly small event on the global scale, but obviously it's a big deal for the people that have been affected. And in terms of Kilauea itself, I would say it's a medium-sized event, medium to small in terms of some of the prehistoric events. In terms of the historic events, it's significant. So my understanding is this new sort of eruption activity started when the crater floor collapsed. Is that correct?
That was more of a symptom of what was happening. That wasn't the cause. And I think what you're referring to was the crater floor of Pu'u'oro. So that was the eruptive site halfway down the rift zone. And the crater floor collapsed because the magma was already being withdrawn from that site. So there was nothing to support the crater floor anymore. It was supported by the magma beneath. So that was the sort of event that made the news to show the world that something new was happening, although the scientists were aware that something was happening before that.
So what was going on that the scientists noticed that obviously didn't make the splashy media?
Well, Kilauea volcano is monitored heavily by the Hawaiian Volcano Observatory. They have over 100 scientific instruments on the volcano. They measure things like gas emissions and ground deformation. So they have, usually using satellites, they can look at if the ground changes by centimeters, and they also measure small earthquakes around the volcano. So as the gas ascends to the magma ascends to the surface, the gas that is dissolved in the magma will exsolve and rise to the surface quicker. So by looking at the different gases that are released, we can tell what depth the magma is at, and obviously if there's new gas in different places, then there's magma in different places. So that's one way they were monitoring what was happening. The second way, ground deformation, if the magma is moving to a new place under the ground, it will push the rock above it up. And likewise, if it's withdrawing from somewhere, the ground will subside. And that was one of the first clues that the magma was being drawn away from these eruptive sites, was the ground deformation looked like the volcano was deflating. And the third sign, these earthquakes, when the magma moves through the rock, punches new paths through the solid rock, it creates lots of little cracks, lots of little earthquakes. And so if we can measure those earthquakes, locate those earthquakes, we can track the path of the magma as it moves. So it's mainly the ground deformation and the earthquakes of seismicity that caused scientists to notice that the magma was being diverted from the two original eruption sites down towards the lower East Rift Zone.
When you say that there's ground deformations, how much change are we talking about here? Is it a couple of inches? Is it feet? How much shift in the ground are we actually seeing?
Well, the instruments that they use can measure down to millimeters, but in this particular event, at the summit, where we're currently still seeing a deflation, the crater at the summit is collapsing, there's been tens of meters of subsidence there.
Oh, wow. So a significant amount.
Yes.
Wow.
Very significant.
How quickly does this happen, this kind of 10-meter subsidence?
Well, that has happened over a couple of months since the eruption started.
Does it happen kind of slowly over the period of months, or is it something that can sort of happens, part of it happens in one go, and then maybe not much movement, and then it happens again in a kind of big burst?
It can do both.
Okay.
It can do both. So if we have a steady magma withdrawal, then you see a fairly steady deformation signal, but you can also have a collapse that is accompanied usually by an earthquake, and so you can see sort of a meter at a time in some places where the ground has just kind of given up and collapses slightly. But in general, it's usually a fairly steady signal.
So what's been causing the fissures? I'm assuming it's where lava is flowing through new parts underground and it's pushing up the earth on top of it?
That's exactly right. Yeah. So the magma has made its way down towards the lower East Rift Zone into the Leilani Estates, and it gets to a point where it's harder to go forward and easier to go up. And it just punches its way through the surface. And because of the way that the magma tends to move in what we call dikes, in a straight line, that's why the fissures are long and thin, and that's why they're all in a straight line. I
was going to ask about that, because you sort of don't really think about it until you see a map that someone's drawn on the island of where the fissures are, and they definitely are in a very clear straight line.
Yeah, absolutely. So that could be because there was some pre-existing weakness. There may have been a pre-existing fault or even a pre-existing magma intrusion there. Mm-hmm. And it means that there was a path of less resistance for the magma to go along, basically.
So it was some kind of path made available to it, even if it's not sort of an open path like a tunnel. It was some way that the lava could get through with less resistance. That makes sense. So how many fissures do we have right now?
I believe that in total there have been 24 fissures.
Are they all still active, or have some kind of calmed down a bit? Well, I know there's others that are still very active.
Most of them have calmed down now. It's fissure 8, which is currently the most active. Over the past couple of weeks, there's been a glow or a very small eruption from some of the other fissures, but the activity seems to have really focused in on fissure 8 to the point where the eruption has actually created a cone around that fissure. So it doesn't look like a fissure anymore. It looks like what we think of when we think of volcanoes. It's got this sort of cone built up around it.
That's interesting. So is fissure 8, is it looking like fissure 8 could continue erupting in this way for some time?
We just don't know. We don't know. There is the possibility that the eruption has slowed down slightly. It's not showing any sign of stopping, but over the past few days, it looks like there may have been a slight waning of the volume of lava erupted.
How quickly did these fissures open up? I mean, do people generally get a warning that a fissure nearby is going to open up? Do we know who to evacuate and how long we have to evacuate them, or is this something that happens quite suddenly?
In this case, we did know. Yeah, the scientists saw that the seismicity had gone down towards the Leilani estates. They saw that the ground deformation was happening down there. There was an inflation. And then they noticed that there were cracks in the road. So they had a few days. They had probably about a week to prepare for the eruption. And then once the cracks started forming and gas started coming out of those cracks, that's when the evacuation started, and they managed to evacuate people who were in the danger zone. So it happens over a few days.
How large is a fissure like fissure 8? It's sometimes difficult to tell in the photos how large these fissures are, or even how much lava is coming out, just because of the way we see them only in photographs. Sometimes it looks like huge, like absolutely massive amounts, because we get these huge overhead shots of sort of lava overtaking houses. And other times you sort of get frames where it's, a person standing in front of what looks to be a sort of small dribble. It's unclear.
Yeah, absolutely. So these fissures vary in size. They can be several kilometers long and several meters wide. I'm not sure of the exact dimensions of fissure 8. Obviously, fissure 8's dimensions have changed because it started off as a long, thin structure, and now, because it's more thermally efficient, the magma or the lava has created more of a pipe, and is coming out in just one sort of circular place. So, I don't know the exact dimensions, but they can be up to a couple of kilometers long and a few meters wide.
There were some news stories about more explosive eruptions at Kilauea, where large rocks were being thrown significant distances. Can you talk a little bit about what caused those explosions?
Yes. So that was at the summit. So that we've got 3 different places that we've been talking about. We've got the lower East Rift Zone, Leilani Estates, where this new eruption has been happening. We've got halfway down the East Rift Zone at Pu'a'o, which is where that collapse first happened, where the lava used to come out, and at the summit, where there was a caldera and there was a lava lake. At the summit, because there was a magma reservoir and this lava lake, when the magma withdrew from the summit, there was deformation, there was deflation there, and as the lava withdrew from the lava lake down the conduit, it was no longer supporting the rock around it. So we had these very steep sides to this fairly narrow tube, and the rocks started falling into the void that was left by the retreating magma. Now, the model at one point was the idea that when the magma got beneath the water table, water was able to seep into the conduit. And when water comes into contact with with lava or magma, it flashes to steam really quickly, and that causes explosions. Or the steam, because the rocks were falling into the conduit, they would form a seal, and the water that was turning to steam wasn't able to escape and would build up pressure, and that would cause an explosion. That was the working model. I think there is now evidence that that's not quite right, but I'm not 100% sure on what the new working model is. But at the time, the explosions are actually ongoing. There's about an explosion a day still at the summit, because the rocks are still falling into the conduit.
Can you talk a little bit about the volcanic gases and fumes that we see coming from Kilauea? In particular, if you're keeping abreast of this in the news, we're seeing the word laze thrown around, we're seeing the word VOG, and I don't know what either of those means.
Yeah, absolutely. So laze and VOG are kind of mashups of everyday words that we're familiar with, in the same way that smog is smoke and fog. VOG is volcanic fog, and laze is lava and haze. So in the case of VOG, VOG is actually something that the people of Hawaii have been dealing with for a very long time. It's basically the plume that's come out from the lava as it's erupting, and it's made up of steam and sulfur dioxide and sometimes carbon dioxide, but mostly sulfur dioxide. And so that can be quite harmful if you have pre-existing breathing problems. It can be really unpleasant if you're caught in it, because it burns your eyes, it tastes horrible, and it makes breathing really difficult. It also affects people further away from the volcano, because sulfur dioxide, when it mixes with water, causes sulfuric acid. And so people experience things like acid rain, and that is very corrosive. So people downwind of the volcano have experienced that they have to, replace their fences very frequently. It can also have a negative effect on crops and livestock as well. But people around the volcano have had to deal with this for quite a long time. Laze is something that occurs only when the lava enters the ocean. What happens, as I said before, when water meets the lava, the water boils very quickly, flashes to steam. And so you can have small explosions when the lava meets the ocean. But in addition to that, a chemical reaction happens, and you get hydrogen chloride in tiny little particles of hydrogen chloride. And also tiny little particles of volcanic glass, so little, almost like ash. And because it's hot, it rises up, and so you get this very dangerous sort of hydrochloric acid and particles of gas in a cloud. And so if you get caught in that, it can be very, very dangerous.
So it sounds like even though the lava is comparatively slow moving, we're not seeing pyroclastic flows with the Kilauea volcano. There is still a lot of hazard with the eruptions that are going on right now.
Absolutely, yeah. So you've got the VOG that you've got to be careful about breathing. You've got the laze that you've got to be careful about breathing. There's additional ash that are coming from the small explosions from the summit. And the ash can also be detrimental to people's breathing. It can be difficult for people's eyes. And it can also really damage infrastructure as well. It can get into the fan on your computer. It can build up in your gutters. And if there's enough of it, if you have a flat roof, it can build up on your roof. And if it gets wet, it's very, very heavy. And so there have been cases in the past at other volcanoes of people's roofs collapsing under the weight of the ash. In addition to that, there are other hazards associated with the actual lava flow itself. Obviously, lava is very hot, can move fairly fast. Luckily, everybody was out of the way when the lava is flowing. There was somebody who had his leg broken because he was too close, and a small bomb is what we call them, like a chunk of lava that got erupted, hit his leg because he was too close to that eruption. And there's also there are other hazards associated with the ocean entry of the lava into the ocean. Mm-hmm. As the lava reaches the ocean, it creates what we call a delta. It creates new land. But that new land is very unstable because it's formed, the lava cools very quickly. It makes it very, very brittle. And so it creates this delta, and sometimes that lava delta will collapse into the sea. And if you're standing on that lava delta, then that's a very dangerous place to be. So the advice is to stay away from ocean entries, from where the lava is entering the ocean.
Is the Kilauea volcano connected to any other volcanoes on the island? Is it something where one volcano that is erupting more vigorously or in a new way can cause other volcanoes to erupt or something like that?
That's a very good question. The answer is probably not. But there has been evidence in the past, people have published papers that show that there might be a deep connection between Kilauea and Mauna Loa, or they might even be sort of anti-correlated, that when Kilauea is erupting, Mauna Loa doesn't erupt, mm-hmm. and vice versa. Those studies are still fairly controversial, but in general, I would say there's not really any connection, because we actually see that the chemistry of the two volcanoes are quite different. So we don't think that they're connected at depth. And there's no connection with Kilauea with any other volcanoes in North America or in Central America. There's just too far away. Volcanoes are a very local phenomenon on a global scale.
That's really interesting. You mentioned their chemistry is different. I hadn't really thought about this, but do volcanoes have basically like a chemistry footprint? Are they each quite different from each other?
They are often very different. I'm not a geochemist, so I can't comment completely on this, but the stickiness of the lava, the viscosity, depends on the chemistry. And but there are also other elements that are present in the lava which are like a signature for each volcano. And there are some elements that are present in Kilauea's lava that are not present in Mauna Loa's lava, and vice versa. And so geochemists know at what depth these elements either get added to the magma or come out of the magma or have certain chemical reactions, and that can tell you quite a lot about the depth that the magma is stored at, how long it has been down there, and the source of the magma as well. So I'm not an expert on that, but it's a really interesting branch of volcanology.
I am so delighted to learn that science continues to do things that I wouldn't have thought possible, like understand so much about a volcano's history and where the lava is coming from and how long it's been there by looking at the chemical makeup of the lava. That really honestly delights me.
Yeah.
So I want to talk a little bit about the cleanup effort, not necessarily specifics on the hows, but let's say the volcano fissures stop erupting tomorrow and the new lava vents stop flowing and people can start to move back in and we can start to sort of deal with what's been left behind. So what has been left behind? When the lava hardens, what's left?
Exactly that. It's just lava. In places it's going to be several meters thick, or more even, and lava does destroy pretty much everything in its path. So houses are going to be flattened or burned, trees are going to be flattened or burned, and what you're left with kind of looks like the moon. It's very barren and just black and bumpy.
Is it like hard rock? What is the texture of lava once it kind of hardens?
It is hard rock, but it's often very bubbly and very cracked, because once the lava starts to harden, any gas that's still trying to escape does get stuck. And so what's left is often very brittle and very bubbly and very cracked. So it's quite difficult to walk on, for example. You've got to be very careful because the shards of the rock are very, very sharp. It's actually glass. It's a type of glass.
Oh, really?
So, yeah. So the shards of this black glass can be very, very sharp. Yeah. So it's very difficult to walk over and to kind of build directly on top of. You'd have to bring in a bulldozer or something to flatten it and to compress it before you can start building.
I'm envisioning kind of like a black glass aero bar.
Yeah, I mean, you can look up pictures of the lava fields because there's a large area that the previous lava flows covered and destroyed quite a lot of homes over the last few decades. And some people have rebuilt their homes on top of the lava, so several meters above where they were, with no trees around or anything, just a house in the middle of this black, barren landscape. It's quite interesting.
So I guess you don't tend to remove all of this built-up lava. I think you mentioned you just kind of steamroll it and make it firm and able to walk on top of or build on top of, rather than actually remove it in any way?
In the terms of in places where there are roads, they will probably remove it, but other than that, no, people wouldn't tend to remove it. There's just too much of it.
So, as just kind of a parting thought, do you have, is this for a scientist quite an exciting period? Are there just, you sort of look at this and go, this is just an amazing opportunity to learn more? Or I guess I'm just curious as to, like, I'm fascinated by reading the news all the time. I was well known in my house for constantly checking on the status of the Kilauea volcano eruptions. I found it very fascinating to watch, in particular because the eruption was so kind of movie kind of, it felt like movie lava. Does that make sense?
Yeah.
Like the sort of lava one only ever sees in movie.
Yeah, absolutely.
And so I found it incredibly fascinating and spent far too long looking up pictures and photos and new videos and all that kind of stuff. As a scientist, do you find yourself captured in that way as well? Or are you more thinking about all of the cool new science that you get to do?
A bit of both. I mean, that's what drew me to volcanology in the first place, was just how amazing volcanoes are and how powerful they can be. And as you said, you know, this is something that is not driven by people, and we can't influence volcanoes. They just do what they do. And so that is, you know, it's a passion of mine, and it interests me and amazes me all the time. In terms of this eruption, it is obviously a really exciting opportunity for us to learn more. And for me in particular, I've got this new project that I'm going to be working on, and I'm going to, you know, add to the knowledge and hopefully help people in the future to learn more, and people who live nearby. So yeah, it's everything. It's exciting in lots of different ways for me. But it is also very sad. We can't ever forget the fact that people have lost their homes and their livelihoods.
Jessica, thank you so much for your time today. Really good talking with you, and I look forward to hearing more about how the new work you're going to be doing in Hawaii upcoming turns out.
Thank you.
If you want to learn more about Jessica Johnson or her work or the Kilauea volcano, we have links to get you started in the show notes for this episode, which, as per usual, you can find on our website, scienceforthepeople.ca. Next up, we take some time to appreciate some of the lesser-known volcanoes found in the USA. Stay tuned.
Science for the People is a weekly radio show and podcast that explores everyday life from a scientific perspective. We are a member of the Skeptic Network, a collection of blogs, podcasts, and video content focusing on science and critical thinking. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to support us at Patreon, to connect with us on Facebook and Twitter, and to subscribe to the podcast in iTunes. And now, back to the show.
This is Science for the People. I'm Rochelle Saunders. With me is New Zealander Dr. Janine Krippner. She's a postdoctoral researcher and passionate volcanologist at Concord University in West Virginia. She studies explosive volcanic eruption products and volcanic ash deposits. She also communicates everything volcanoes on Twitter, with media, and on her blog because she saw for herself how crucial it is to reach people through these platforms during the Agung volcano crisis. Welcome to the show, Janine.
Thank you very much for having me.
So before we get to some of the U.S. volcanoes, which is what I wanted to talk to you primarily about, because it was in the introduction, can you talk a little bit about the Agung volcano crisis?
Yeah, sure. So I've been on Twitter since 2013, just tweeting about volcanoes and eruptions. And on the 22nd of September, at the end of last year, Agung volcano was raised in the alert level. And so I was tweeting about it like any other volcano, and a friend of mine let me know that they had no idea what was going on in Bali, like the tourists and the people living there who are expats, so from countries like New Zealand, Australia, the UK. So this kind of exploded in the media without an actual eruption for 2 months, and I just communicated the official information in English. And it ended up getting used a lot by the media. I did a lot of interviews. So it really changed my life a little bit and my career, in that I've got this focus in communication now.
That's amazing. So I know that this eruption, it was quite well publicized, and there was a lot of concern for the people in that area around the volcano as well.
Yeah, and the concern was quite misunderstood. So there were a lot of people, I think around 120,000 people evacuated from the immediate vicinity. But with volcanoes, the further away you go, the hazards change. So while there was risk of flight cancellations and volcanic ash, which is not good if you have respiratory issues, there was a big misconception that the whole island was going to be destroyed effectively, which was not and still is not the case.
That's interesting. I think there's a lot of misunderstanding that goes around with volcanoes, because volcanoes are such massive, kind of unstoppable forces of nature to us. And also the volcanoes we tend to think about are the ones I guess we see in movies, the kind of big dramatic volcano eruptions that tend to destroy massive amounts of space. I'm just trying to think. There's probably not a lot of really good detail I have about what is a typical volcanic eruption. My assumption would be that potentially the entire island was in trouble.
There really is no one typical style of eruption because each volcano is different. But I noticed it was really interesting that people either thought it was going to be extreme, like a big caldera collapse, which is actually quite a rare event, or a Mount St. Helens style eruption where the eruption went sideways. And once it actually did start erupting in October, November, it was producing this fairly decent ash plume, but I was still getting asked, when is the volcano going to erupt, because people couldn't see lava. So I was like, this is an eruption, people. This is it.
It reminds me of some of the stuff that's going on at Kilauea in Hawaii right now. We see these dramatic images of these what appear to be just massive sort of rivers of lava that are taking down houses and things like that. And we sort of close our eyes and see this as something that's affecting the entire island. But when you actually kind of zoom out and look at the effect and what's happening on sort of to scale in the island, it's actually quite a small area of the island that's being affected. Not to understate the impact there, but it looms very large in our imagination, because compared to the things we see every day, like a house, it seems incredibly massive, but we also have to factor into account the size of islands or the size of spaces as well.
Yeah, definitely. The gas impacts are definitely wider, but the lava flow itself is not that much of a big area. So yeah, you're right. The misconception of just the really impacted by lava size of this area is a lot smaller than people think.
So I do want to talk a little bit about some of what I would consider to be the underappreciated volcanoes in the U.S. I think there's a few that everybody knows about. Everybody knows that there's volcanoes in Hawaii. There's a lot of tourist trade that goes on in Hawaii. And I think that probably everybody's familiar with Mount St. Helens. That is a fairly well-known volcano. There was a big eruption that happened there. I think it was in the 80s. Is that correct?
Yeah, 1980. The really big eruption was in May, on May 18th. And there was also an eruption period in the 2000s, so from 2004 onwards for a few years, which produced some ash explosions and a lava dome, which is a more solid style of lava or magma that comes up and kind of builds a solid pile in the crater, and these can collapse to cause pyroclastic flows or ash plumes, which occurred during that eruption. So that's a more recent eruption on the continental lower 48 that most people aren't aware of.
That's interesting. I'm not sure that I was aware that there had been a more recent eruption at Mount St. Helens. It just goes to show how some of that stuff just gets kind of filtered out of our brain unless it reaches a certain kind of peak disaster, which sounds terrible, but it's probably true.
Yeah, you're right. We don't remember everything that we should, and we remember things very different to how they actually happened.
So I do want to talk about some of those lesser known volcanoes, because I think those ones sometimes get to steal all the glory. Let's talk a little bit about the Cascade Volcanic Arch, which is a kind of area of the U.S. where a lot of the volcanoes that there are in the continental states, where they tend to be. Can you talk about where that area is for people who've never heard of this spot?
Yeah, so the Cascades is a chain that runs from northern Washington all the way down to northern California. So there are a few volcanoes in California that are actually included in that as well. But the bulk of it is running through Washington and Oregon. And we have a lot of big volcanoes that people are aware of, like Mount Hood, Mount St. Helens, of course, even though that kind of blew half its top off. There's Rainier, which a lot of people see from Seattle when it's not cloudy. And then there are volcanoes like Glacier Peak, Mount Baker, Mount Adams, Mount Jefferson, Three Sisters, Newberry, Crater Lake. So there's a whole bunch of these big volcanoes. But even though there are a lot of really big volcanoes, there are many, many more smaller volcanoes that most people don't particularly know about. So there are a lot of big ones, but even more smaller ones.
So before we talk specifically about some of these volcanoes, why is this area such a hot spot for volcanoes? Is this an area where plate tectonics comes into play and is sort of pushing up and making these spaces more volcanic? Or is this more of like a Hawaii-like hotspot where there just happens to be sort of magma closer to the surface?
The Cascades themselves is a subduction zone. So that's when you have a much smaller plate that is going down underneath America. But there is a hot spot nearby, and that's what we see at Yellowstone. And then further down in California and also inland, there's extension where the plates are being pulled apart and thinning, which makes magma closer to the surface, or heat closer to the surface, I should say, which can then result in lava forming.
So let's talk a little bit about Mount Rainier, because that one is one that I've seen, and one that kind of looms large in my memory from my visits to, I think it's near Seattle, isn't it?
Yeah, the Seattle-Tacoma area. So it's a little further south of Seattle, but it's southeast of Tacoma.
So how active is this volcano?
It's not too active right now, but it is definitely a threat, and it doesn't have to be active to be a threat. And that's because it has a very high risk of producing lahars or volcanic mud flows. And while these can be formed by even very small eruptions, putting hot material on all of those glaciers and snow and ice that are on Mount Rainier, it can also occur from flank collapse or parts of the volcano that have been weathered over time falling away. So that's that's probably the most dangerous volcano in the United States.
That's interesting. So people would probably think of something like Mount St. Helens, or if they know about the sort of Yellowstone caldera as those being the most dangerous. But Mount Rainier, even though the danger doesn't necessarily come from something like huge explosions or pyroclastic flows, it does seem like it's got some more mundane but more likely things that can cause a lot of problems.
Yeah. So Yellowstone usually gets all the attention, but those really big catastrophic eruptions that produced at Yellowstone are actually very rare. So that kind of takes that out of the picture in a very big way. And Mount St. Helens, we've definitely seen what that volcano can do, but that's in a national park. It's not in a very populated area. And while that can still produce lahars that can go downstream as well, Rainier, there are about 80,000 people and their homes at risk in that area. And then there are highways and utilities and all of those kind of things, hydroelectric dams, seaports that are all at risk if a big lahar occurs at Rainier. So it's one of those things where you have to be prepared for it because the impact can be so big.
So moving away from Mount Rainier, can you talk a little bit about South Sister? I know that this is part of a grouping of 3 peaks, or are they all volcanoes?
They are all volcanoes. They're actually all sort of separate volcanoes. They react differently. But South Sister has had one of the most recent eruptions, and it was about 2,000 years ago.
Whereabouts are these 3 peaks?
These 3 peaks are about 35 kilometers west of Bend and about 100 kilometers east of Eugene. And it's a gorgeous area. If anyone listening hasn't been there, go and check it out. It's beautiful.
So when you say that there had been, I think you said an eruption about 2,000 years ago, what kind of eruption was this?
The eruptions at South Sister, they can be more, the North Sister, Middle Sister, and South Sister, they erupt in different ways. So the North Sister is more basaltic, so we have 3 different kinds of magma. Basaltic is what we see at Kilauea. So it's a lot more runny. The gases, which are very important in eruptions, gases build up pressure if they can't escape easily. They can escape a lot more easily in a basaltic runny lava. Then we have andesite, which is kind of your intermediate, and that is usually quite explosive because the gas can't escape. And then we move up to rhyolite, which is the most sticky or the most viscous magma type. And if it has trapped gas, it can be very explosive, and if it doesn't, it can just form silicic lava flows, we call them. So high silica content, that's what defines these different lava flows. So South Sister has these stickier, more viscous lavas.
What makes those more viscous lavas dangerous?
It does depend on the gas content. So if it doesn't have a lot of gas built up, if the gas is slowly released over time, they can just produce lava flows, which has happened in South Sister. But if they do have a lot of trapped gas, you can kind of think of it like shaking up a bottle of Coke. So there's a lot of gas that wants to come out, but it can't. And then taking the pressure off that by taking the cap off the bottle of Coke, it blows the liquid or the Coke apart because the bubbles are expanding so rapidly now that they can. Well, that's what can happen when you get very viscous, gas-charged magma to the surface, is it can all of a sudden release and it blows the magma apart in these very ash-rich eruptions. But this doesn't always happen. You can get very thick lava flows, or you can get volcanic domes. Again, so that's a plug of magma that rises up almost vertically out of a volcano. Now, those can produce pyroclastic flows, so they can also be very dangerous. And what a pyroclastic flow is that's an avalanche. It's basically an avalanche that is extremely hot. They can move extremely fast, and they race down the volcano. And above them, you get these billowing volcanic ash plumes. So very, very dangerous.
When was the last time we've had a pyroclastic flow in the U.S.? Is that Mount St. Helens, or has there been a more recent one?
That was Mount St. Helens, yeah. The 1980 eruption, there were several eruptions, actually. There was some in June and July, and some further ones as well that produced smaller pyroclastic flows. But the largest was on the May 18th eruption in the afternoon of that day.
So with South Sister having maybe a higher potential to explode, are there places nearby where that makes this a dangerous volcano, or is it sort of sufficiently isolated that this becomes a little bit less of a disaster problem?
Well, first of all, an eruption is not likely in the future. So
that's fair.
It's being monitored. In fact, there was some uplift or deformation around 2001, which could have been magma, but it could have also been fluids moving under the volcano too. But because of that, they've done a lot more work on this volcano. They're monitoring it closely, and at this point, an eruption is unlikely if everything continues the way it is. But with Three Sisters, because there aren't people actually living on the volcano, there is a danger of lahars. So if there's a lot of snow and ice in the area or high rainfall, you can entrain a lot of loose volcanic material into these mud flows like Rainier, but not quite on that size scale.
Is there somewhere in the Cascades a volcano that people are most concerned about, or something there where we are seeing some activity or some ground deformation that indicates that it might be getting ready for an eruption?
Not at the moment, no. And USGS will absolutely be telling people if that's the case. There are relatively frequently, seismic swarms. So with volcanoes, when you have magma and fluids that are going through these systems, which is quite normal in potentially active volcanoes, and there are a lot of those in the US, rocks can break, and and you can actually measure the movement of these fluids. So you can have swarms, which is an uptick or an increase in the seismic activity, which is picked up by monitors around the volcano or in the region. And these do happen every year or so. I think I see them pop up in the news, but USGS always gives people notice of, hey, we're seeing an increase in activity, but this doesn't mean that anything is about to happen.
So is that just a cue for people that, something's happening, we're being transparent, you shouldn't need to worry? Is there any desire for people to maybe pay a little bit more attention in that when they see those kinds of warnings, that something might potentially happen later they should pay more attention to? Or is that just kind of the normal communication of science continuing to be transparent and open and say, hey, we noticed this activity, but there's nothing for you to worry about?
Yeah, it's definitely part of being transparent and having people realize that these are active volcanoes. Some of these events are telling us that way down below the surface, magma is moving. It is there. But the USGS does have the volcanic alert level system. So so far all of them are on green in the Cascades, so that's normal. If that then raises, then people should start to pay attention. But there's a lot of work that goes on behind the scenes with USGS working with local governments and emergency managers so people get prepared for these kind of events.
So when we look at the kind of peaky volcano type, which everyone closes their eyes, thinks of as a volcano, knows as a volcano, and we transition to thinking about a caldera volcano, something like Yellowstone, which is very much a kind of large caldera. I think there's one at Crater Lake as well. Is that correct?
Yeah, Crater Lake is a caldera, and there's also Long Valley caldera in California as well. There's a few others too, but those are the more well-known ones.
So those are a very different kind of geography. We're not talking about something tall and peaky. We're talking about something that's bowl-shaped, correct?
Yeah, and usually those don't start out as a peaked volcano, but Crater Lake or Mazama, which is the name of the volcano, actually did.
Oh, so it started out as, right, you were saying it started out as the peaky one and then became, sort of fell away and sunk and became a more crater, sort of caldera type volcano.
That's correct.
So what is the danger of those kinds of volcanoes? Are those likely to create something like pyroclastic flows, or do those have an entirely different kind of eruption profile?
The thing to keep in mind is that these big caldera-forming events are actually more rare. So generally speaking with volcanoes, the smaller the eruption, the more frequent it is. And that's because it's easier to have a smaller amount of magma erupt than it is a really big magmatic volume. So at Crater Lake, the eruption that happens 7.7 thousand years ago is unlikely because that amount of magma aren't available, as far as the geophysicists know, to cause an eruption like that. So to get these big eruptions, you have to have eruptible magma sitting there that's about ready to go or almost ready to go. So they can also, these big caldera-forming volcanoes, the term supervolcano is thrown around a lot. Usually they produce a lot smaller eruptions, much more frequently than these really big events. And that's the same scenario at Yellowstone. So Yellowstone's more likely to produce a lava flow than anything else. And the recent eruptions at Crater Lake, there's Wizard Island in the middle of it, and there are a few lava flows and domes down underneath the water that have occurred since then. So there are lava flow eruptions when you get that sticky lava that's not gas charged that I mentioned before, that can produce these lava flows and domes which aren't as explosive, anywhere near as explosive as these big caldera forming events.
So these calderas, I guess they just are sort of more likely to have, I'm thinking of them as almost valves. So these weak spots that they can eject little bits without causing a big explosion. So they can kind of let off some of that early pressure so the pressure doesn't build. Is that kind of a good way to think about it?
I'm not actually sure.
Fair enough.
Maybe, but the timescales are so different.
Mm-hmm.
So these smaller eruptions can happen more frequently, and then over time, and I'm talking like tens of thousands of years or even more, that it takes to build these big eruptible magmatic systems. I'm not sure how many smaller eruptions you'd want to offset that, but yeah, I don't know. That's complicated.
Volcanoes and science, so complicated.
Yeah, any good volcano answer starts with "it depends" and it's complicated.
That's amazing. I think most good science answers start out with "it depends" and then ends up with "it's complicated." So that makes me feel like there's solid science at the heart of our knowledge of volcanoes.
Yeah. In fact, the more we know about how much variation there is, and the more we know that it depends and it's complicated. So if there's a simple answer, it's, well, do we really know everything about this?
Yeah, like there's you've built up this wariness of the simple answer of like, that's a symptom that we haven't looked at this closely enough, probably.
Yeah. Like if you're looking at volcanic unrest, which is when there's an increase in activity that may or may not lead to an eruption, and you get more monitoring equipment in there, we know now that a volcanic system can increase in activity and then decrease, and increase and then decrease, and then mess with us for weeks or months, and then lead to an eruption or not. Or they could ramp up really quickly over days to an eruption, or they can be just about ready to erupt and then stop. So the more we know about this variation, the more cautious we are.
That's fascinating to me. And also it must be really sort of tense and frustrating and also kind of fascinating for scientists who are studying these kinds of things when there is activity, but you're not sure what it means. That makes me fascinated, but also concerned.
Yeah. And sometimes you really can pin it down to what might happen. And volcanologists, we don't predict eruptions. That's saying that a volcano will do this thing at this time on this day. We don't do that because we know there's so much variation. But volcano observatories can give forecasts. So that's saying there's a chance of this happening within this time period. And we saw this before the Kilauea eruption. The Hawaii Volcano Observatory did an amazing job monitoring this volcano and understanding the past eruption activity. So when they saw an increase of activity heading down the East Rift Zone, they said something could happen within this time frame. Something did. And then before the explosive summit, even though it was quite small, the more explosive summit style eruptions, they gave warning for that too. They also gave warning that the eruption was probably going to get worse because fresher, hotter magma had not erupted yet. So there is a lot of good information that you can get if you understand a single volcano, and if you've been monitoring it for a while, and if you've done a lot of work to understand what that eruption has done, what that volcano has done in the past.
So it sounds like what's really important is for scientists to build up a familiarity with a particular volcano, that volcano's chemistry, that volcano's makeup, that volcano's history, to help them understand better what that particular volcano will do, rather than go to another site and think like, well, these other 4 volcanoes did X, so this volcano must do X.
Yeah, exactly. And knowing what other volcanoes do definitely does help. It all adds to the story and the understanding of what volcanoes are and what they do. But if you don't understand a single particular volcano before it erupts, once it starts showing activity, you're playing catch up the whole time. So waiting until the activity is ramping up means that the volcano observatories are trying to get equipment out there, trying to get that equipment set up, as well as looking at the geology and playing catch up. And this is with a dangerous, deadly force of nature. And it's not only them, it's the emergency managers who may or may not have plans in place. It's first responders. It's all of these different moving parts with a potential time bomb, and you can't see the timer.
On that note, Janine, thank you so much. This has been really fascinating, and you have a absolutely fascinating job that I think many of us, both adults and the child version of ourselves, are very jealous of in a lot of ways.
Yeah, I still, in many ways, can't believe that I actually get to do this. So I decided I was going to be a volcanologist when I was 13, and I loved volcanoes my whole life. So I'm incredibly grateful to be doing this.
If you want to learn more about Janine Krippner or her work as a volcanologist, we have links to get you started in the show notes for this episode, which, as per usual, you can find on our website, scienceforthepeople.ca. Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessica Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skepchick Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by science news writer Bethany Brookshire and me, Rochelle Saunders.